Thank you for a great introduction. My today's talk is about adversarial robustness. I'm going to cover two aspects, background knowledge and two case studies on how to apply the adversarial robustness. Let's go to the point one first. Adversarial attack can evaluate the vulnerability of machine learning model. Why? It is because machine learning models are very sensitive to the input perturbations. For example, with only small noise, the image of pig will be wrongly recognized as an airline. How to construct the adversarial data? We basically solve a constraint optimization problem. Given a machine learning model and its loss function, we output an adversarial data, maximizing the loss within the null-ball constraint. The null-ball constraints the same semantic meaning between adversarial data and its natural data. The epsilon controls the size of null-ball. Project gradient descent, PGD, approximately solved this constraint optimization problem. Given a starting point, PGD calculates the gradients of this loss function with respect to the input. Gradient is a direction pointing to a place with a slightly larger loss. Now, we get a new point whose loss is slightly larger than the natural data. Then we calculate the gradient again. The loss of yellow point is again larger, so on and so forth. Finally, we get a red point, which can make machine learning model inaccurate. Why the machine learning model are so vulnerable to adversarial attacks? It is because standard training outputs a model whose decision boundary is near the data. Therefore, when we slightly perturb the near decision boundary data, the model will make mistake. Even worse, due to the curse of dimensionality, almost all data are near the decision boundary. To meet the above challenge, we have a new style of learning strategy that is adversarial training. Adversarial training has two purposes. First is to correctly classify the data, that is increasing natural accuracy on natural test data. Second, unlike those standard training, adversarial training outputs a thick decision boundary whose data are further away from the decision boundary. The learning objective of adversarial training is min-max formulation. Inside, there's a maximization. We commonly use PGD to generate the adversarial data within the null-ball. Outside, there's a minimization, where we find a classifier to fit those generated adversarial data. To realize this learning objective, we use alternating optimization technique. At each epoch, adversarial training conducts step 1 and step 2 alternatively. Step 1 to generate the adversarial data using PGD method. Step 2 is to minimize the loss on the generated adversarial data. In comparison, at each epoch, standard training minimize loss on the natural data with respect to the model parameters. Next, I'm going to cover two case studies on how to apply the adversarial robustness. We understand that adversarial attack is a way of uncovering the vulnerability of machine learning model, and adversarial training is a way of making those machine learning model robust against those attacks. Therefore, I will show two case studies using the attack to evaluate the vulnerabilities and using the adversarial training to enhance the adversarial robustness. I'm going to give two examples, deep image denoiser and non-parametric two-sample test. Image denoising is reconstruct the clean image from their noisy observations. Therefore, it is commonly used in medical image, satellites, and camera. In image denoising, the noise is generally considered to be a random variable with zero mean. For example, if we can take a large number of pixels and compute their average, the noise should be cancelled out. Otherwise, the noise will affect the brightness of the image. Because of this zero mean property, traditional method in OpenCV commonly use the non-local mean denoising. The idea is simple. Given an image, we find a similar patches, then average out the noise. Now, we go to the machine learning time, and we need to learn a good image denoiser. Specifically, the image denoiser is denoted as a deep neural network, taking input the noisy images and giving output a clean image. However, in practice, we only have clean images as the training data. To solve this, we construct the noisy image by adding Gaussian noises with zero mean of various levels. Then we can have a deep image denoiser that can perform much better than the non-local mean denoising method. However, although deep neural network has good performance, it is vulnerability to adversarial attacks. Similarly, this also applies to the deep image denoiser. To explore this, we ask a research question. What kind of zero mean noise that makes deep image denoiser fail? To answer the above question, we design zero mean adversarial attacks to evaluate the vulnerability of deep image denoiser. To realize this attack, we use PGD method. But this PGD method have to meet two constraints, which is different from the conventional one. First, the noise should be bounded by the adversarial budget. Second, the noise should meet the zero mean property. To realize this, we customize the projection function in the PGD method. And the most interesting part is the projection pi that meets the two constraints. To meet the zero mean property, the projection function pi should project the adversarial noise onto the zero mean plane. The zero mean plane consists of vectors z whose means of its elements equals 0. How could we project a vector delta onto a plane? First, we're going to find an all one vector that is orthogonal to this plane. That's the zero mean plane. Then we project a vector delta along the direction of this all one vector. Then the adversarial noise delta minus this new projection leads to a new vector that is on the zero mean plane. Therefore, the black vector is what we want. Now, we have our two-step projection pi. The first step is to meet the zero mean constraint. The second step is to meet the adversarial budget constraint. For example, we can see here, the deep image denoiser can effectively handle the noisy, normally noisy image and remove the noise to reconstruct the clear images. By comparisons, if the noise is crafted by our zero mean attacks, the performance of the deep image denoiser is severely destroyed. We can see some blurs on the roofs and some strange contours in the sky. Therefore, our zero mean attack can indeed uncover the vulnerability of deep image denoiser. Next, can we make the deep image denoiser robust? The solution is adversarial training. We add an additional loss term to encourage the output of adversarially noisy image to be similar to the output of normally noisy image. Therefore, we train a deep image denoiser using both adversarially noisy image and naturally noisy image to ensure the reconstruction quality is high and the reconstruction is robust. To realize this learning objective, we alternatively use the PGD method to generate the adversarial noise and then minimize the above two loss terms with respect to the model parameters. Then we found, compared to the standard training, our adversarial training can ensure the reconstruction quality under attacks. Last but not least, we surprisingly found that robustness of deep image denoiser can also benefit the generalization capacity on unseen real-world noise. In other words, the robust deep image denoiser can denoise the real-world noise even without training on the real-world noisy image. We guess it is because adversarial attacks can exploit the worst-case noise. Learning from those worst-case noise can make deep image denoiser deal with various types of unseen noise. I saw some questions on the chat box. I'm going to answer it later. Yeah. Okay. Let's look at another example. Two-sample test. Two-sample test is a statistical hypothesis testing, judging whether the two sets of samples are drawn from the same distributions. It is widely used to analyze the critical data in physics, chemistry, biology, so on, to check whether their scientific experiments have made significant changes or not. How to test? We firstly define a test statistic. The test statistic measures how different the two batches of data are. Then we compute the p-value. P-value is the probability of observing this test statistic given the null hypothesis. The null hypothesis means the two distributions are the same. If this probability is very low, we're going to reject this null hypothesis. Let's look at an example. We have two batch of apples of various size from two companies. We really want to know whether these two batch of apples have the same quality. Firstly, we calculate the test statistic. This is a t-test. XP bar is the average of these 5 apples. SQ bar is the average of these 5 apples. Sigma P is the standard deviation of these 5 apples. Sigma Q is standard deviation of these 5 apples. NP equal to 5, NQ equal to 5. Suppose we get a value of minus 2.44. We really want to know whether this value is large enough to tell any differences. Therefore, we look at the distribution density function of this test statistic. We found that the probability of this test statistic under the null hypothesis is very low. For example, probability is 0.024. Then we cannot accept. We have to reject the null hypothesis and conclude that these two batches of apples are different quality. In practice, t-test is very limited, which cannot handle the complex distributions. Therefore, we need to use the general purpose test statistics. However, computing quantiles of general purpose test statistics under the null hypothesis is very tricky. To solve this, we estimate the quantiles using the permutation test. Under the null hypothesis, we randomly shuffle the joint set of SP and SQ into S1 and S2. We can treat S1 and S2 set coming from the same distribution. And then we compute the test statistic of S1 and S2. Then we repeat. For example, we repeat this process 1,000 times. We can plot the empirical CDF of this test statistic under null hypothesis. Finally, we can locate our test statistic of SP and SQ here. 1 minus this value is our calculated p-value of this test statistic. Now, I will introduce a general purpose test statistic, maximum mean discrepancy, MMD. MMD measures the differences between distribution of P and Q, which is the largest differences in expectation over all functions. However, we have limited data. We must restrict the function class to provide powerful finite sample estimates. But we also want this function class to be rich enough to be flexible. Therefore, we choose this function class F to be the unit ball in a reproducing kernel Hilbert space, RIKEN-AIP. Then we define the kernel mean embedding to embed the distributions into infinite dimensional feature space. This can allow us to compare and manipulate the distribution using dot products. And due to the reproducing property in RIKEN-AIP, we can make the soup disappear and use the kernels to calculate and compare two distributions. If the MMD equal to 0, the two distributions are the same. We actually can use the many and different estimation to estimate the MMD. let's make notation simple. We denote MMD square hat estimation by kernel K parameterized by theta, like this. Then how to test? First, we fix a kernel and its parameters, such as Gaussian kernel and its length scale. Then, given ST and SQ, we calculate the estimation of MMD. This is test statistic. Then we use the permutation test to estimate the p-value of this calculated test statistic. Lastly, we're going to reject the null hypothesis if this p-value is too small. Otherwise, we accept the null hypothesis. Now, we go to the machine learning time. We should learn the kernel parameters from data. We can use deep kernels, and the theta is parameterized by a deep neural network. How to learn the parameter theta? First, we split the data SP and SQ into the training set and test set. Second, we define a learning objective and optimize the deep kernel. Then we conduct two sample tests using these optimized deep kernels. The next question is how to define the learning objective for learning the optimized deep kernel. The learning objective is the test power. The test power is the probability of rejecting the null hypothesis, and the alternative hypothesis is true. Due to the asymptotic of MMD and the alternative hypothesis, we use the central limit theorem. R is the rejection threshold decided by the permutation test. Big sigma is the CDF of standard normal distribution. Then for large N, the test power is dominated by the first term. To compute the first term, we estimated using the kernel operations, which is parameterized by the theta. Finally, we can obtain the optimized deep kernel by maximizing the test power on the training data. Then the two sample test will have a very powerful testing ability with this optimized deep kernel. Now, we consider a potential risk that causes a malfunction of a non-parametric two-sample test. To this end, we use PGD method to minimize the test power to search for the adversarial test pairs. For example, we have a lovely image of cats and dogs. The non-parametric two-sample tests can correctly differentiate the benign pairs of cats and dogs coming from the different distributions. But they will wrongly judge the adversarial pairs coming from the same distribution. Almost all the two-sample tests think this dog and cats coming from the same distribution. Clearly, this is wrong. To robustify the non-parametric two-sample test, we propose to adversarially learn the robust kernels. In particular, this defense is formulated as max-min optimization which has a similar taste of adversarial training's minimax formulation. For its realization, we interactively generate the adversarial pairs by minimizing the test power in inner minimization and update the kernel parameters by maximizing the test power on the adversarial pairs in outer maximization. Therefore, we can obtain the robust kernel. And two-sample test with a robust kernel can resist against adversarial attacks while maintaining the good test capacity. The take-home message is traditional method has limited performance. Recently, we have machine learning method which have good performance but are vulnerable. Now we really should have robust machine learning methods that have good performance and are robust. Thank you. If you have any questions, please feel free to open your mic to ask. I saw some questions on the chat box. How to define the failure of the denoising task? Basically, they have some scores. They have some scores on define the success of the denoising. That means the comparison between the clean image and noisy image, reconstructed image. For example, the MAE error. We basically can use this metric. If this error become larger, we can see the reconstruction quality is damaged. So yeah. Hope I answer your question.
Thank you for answer. So may I speak directly? So I think, can you hear me, Jingfeng?
Yes, I can hear you. I can hear you. Yeah. So
unlike the classification problem, we can easily see that your attack is successful if the classification label is wrong. But for denoising task, I think the reconstruction error, it's not easy to see this attack is successful or not. So I just curious how you define your attacker is successful. Do you need some kind of threshold to
you can think about this? There are no such threshold. You can think about the loss, like regression loss. If your attack can make the regression loss significantly bigger, we can be confident that the attack is very effective. So yeah, we don't have the threshold to judge. When this is large enough, we see this is successful. We can see here the attack is effective. Yeah.
Okay, so thank you.
It's also applied to here. Yeah.
Maybe may I ask another question? So sure. I think you use deep learning to do denoising, and when you do the training, you assume the noise is Gaussian distribution, right?
Yeah, follow others works.
Yeah, right. But when you do attack by adversarial attack, I think you put a perturbation which is not follow Gaussian distribution. That's why the result is. Yeah. So how about if you train your model again by like new distribution noises?
That is what we did actually, because the noise in the deep image denoising have to meet the zero mean property. That is like this. Otherwise, the noise will affect the brightness of the image. Therefore, our adversarial noise also have to meet the zero mean property. So to make it robust, actually, this is what we did in our adversarial training strategy. This is follow the Gaussian noise. this follow the adversarial noise that is coming from the new distribution. Just now you mentioned. Therefore, just adding a new loss term to encourage the adversarial noisy image to be similar to the Gaussian normally noisy image. Yeah, this new term, loss term.